Hi, this is Anchit. So, based on the paper I read recently on acoustic metasurfaces, I would like to review a few of the topics related to it. So, firstly, I'll come to the literature gap that the papers identified. So, the paper basically attempts to address any limitations in the present day passive acoustic metasurfaces because they're largely inflexible and are unable to modulate the acoustic response on demand. So, there are metasurfaces that can be programmed today, but most of them are active using transducer arrays. And these are very expensive options. So therefore, they're generally they're not in vogue in the acoustics domain. So it's very important to identify a more cost-effective approach for programmable metasurfaces so that we can achieve applications such as acoustic imaging, levitation, and communication. So the authors of this study, they propose to implement passive acoustic metasurfaces, which they will program using unit cell arrays. And these unit cell arrays are programmed using five shunted Helmholtz resonators. And these Helmholtz resonators, their cavity sizes are controlled by varying the amount of fluid that passes into or out of the unit cell. Now, what is the most important physical principle that's involved here? So, the most important principle for the programmability of the system is actually the height of the cavity and how you vary the height of the cavity itself. So the height of the cavity is varied using a controlled fluidic system that basically pumps liquid into and out of the cells, and it helps achieve various functions. So firstly, complete phase modulation between minus pi to pi. You also have a very important switching function of the cell wherein you can vary the transmission coefficient with cavity height. So, for instance, if you achieve the maximum cavity height of the Helmholtz resonator, the transmission coefficient will sharply drop to zero since you're nearing the resonant frequency. Now, if we come to the future scope, or what are the other implications of this study? Well, firstly, this could be used for bianisotropic metasurfaces, which are useful for asymmetric reflection and transmission, and also they also have the switching ability demonstrated, which can help in applications such as beamforming, which is essentially a form of wireless communication. And last but not the least, a lot of the applications that I mentioned at the start of the video, which are levitation, acoustic imaging, and acoustic communications. So there's a lot of future scope for metasurfaces. But if I come to my own research area, so currently I am developing acoustic signatures for an axial server fan and trying to implement acoustic mitigation techniques since centers have a lot of noise. Now, my focus so far has mostly been on acoustic insulation materials, but the fluidic system of the Helmholtz resonator is a potential option given that I could use it to minimize my transmission coefficient by varying the cavity height and also use the steering property of the resonator so that I can steer the waves towards insulation materials such as baffles. So that's all from me today. So thank you.